Welcome again in continuation about the sampling distribution. So we were discussing about sampling distribution by means where central limit theorem could be applied. But there are certain conditions where we cannot apply if sample size is small or the source property, which is the variance, is generally not available as a knowledge to the engineer. So in that case, we take the help of two types of distribution which are named as T distribution, which is a sampling distribution by mean for lower sample size, and a chi-square distribution, that is a sampling distribution by variance, where we compare the variance of the sample with respect to the source. Now this is what we call sample. Sample is nothing but which is taken out from the population. If the size is small as n equal to 2, so the sample has very small. So in this case, the source has the properties mu and sigma square, and the sample has the property x bar and s square. When we transform this distribution into a sampling distribution is nothing but a relationship between probability and a random variable. If probability and random variable is your x bar instead of x, then this is sampling distribution. So sample is giving us the properties mean as x bar and variance as s square, where n minus 1 is called as degrees of freedom. As per the number of group of samples, the degree of freedom is this. So there is one group of samples, so n minus 1 is the degrees of freedom. So in this case, we are going for applying the T distribution and chi-square distribution. As we know, the distribution is nothing but the relationship of random variable with respect to the probability of random variable. So this random variable is nothing but what we call statistics, and statistics of this is making a distribution. So this relation is a distribution and this is random variable is a statistics. What we see over here, sampling distribution of important statistics allows us to learn information about the parameters. For example, an engineer is knowing the certain type of resistor. The sampling distribution of x bar will be exploited when the sample information is gathered. On the other hand, if the variability of the resistance is to be studied, the sampling distribution of, if variability is studied, as I gave the example of iPhone, where variability is important, then we have to take the information s square from the sample and compare it with the source variance. But in case average is important, we will compare it with respect to the source mean. So these are the cases where we can have the sampling distribution. Now why do we use sampling distribution by means or variance? So now in case of relationship between probability and versus random variable, if random variable is based on the sample and sample has a specific size n, then this relationship is called as sampling distribution. Generally, we do not make a decision based on taking out one item from the source and we compare this whether this belongs to the source properties or not. It is only possible when we have set of items from I equal to 1 to n. So that become a sample, and sample is compared with the source. So that is the way we take the advantage of sampling distribution. We have learned one kind of sampling distribution where by means where the sample size is large, we could apply normal distribution based on central limit theorem. But when this sample size is not large, we could not apply normal distribution and we have to go for other distribution, that is called as T distribution. Now if we are talking about the variability, if we have to compare the variability of the sample with respect to the source, Then we take the sampling distribution of S square. Sampling distribution of S square will be nothing but relationship of S square with respect to the probability with respect of S square. So because variance cannot be less than 0, so this distribution will be between 0 to infinity, and that may have any kind of shape. That shape generally changes with respect to the sample size. If sample size is small, 1, or sample size is 2, or sample size is 10, the shape changes towards this kind of transformation. What is the basic concept of chi-square distribution? Chi-square is a distribution where relationship of source and sample is such that if xi is or x1 is an outcome from the source, if we plot the relationship of this outcome with respect to the probability of occurrence of this outcome, this will become a distribution. Suppose we have a standard normal distribution for x as n 0, 1, which is transformed from an x distribution that had a normal distribution having mean as mu and variance at sigma square. So if we have transformed into n distribution, and suppose we have a new random variable or transform variable as q1, which is nothing but the square of x. So if it is the square of x, its degrees of freedom equal to 1. So in this case, the distribution with respect to q1 will be something like this. It will have a kind of, so if the value of x is very small and we square it, it will become very smaller. So in that case, it will become a kind of infinity relationship towards 0. Now if suppose a new random variable q2, which is square of 1 outcome plus square of 2 outcome, so that case degrees of freedom is 2. So in this case it will be slightly larger, so the distribution will have something shaped like this. So this will be for q2. If suppose there is a new random variable q3 where 3 items squared sum is used, so in this case the shape will become something like this. If it is more, then the shape will turn out to be like this. So in this case, this is called as chi-square distribution. So this is the basic concept of chi-square distribution, which we apply in case of variability to be compared with respect to source variance, which is nothing but sigma square. So chi-square concept is the square of the random variable and then how many disks are there depending upon the sample size. This distribution, which transforms the source distribution into some other distribution, is called as chi-square distribution. Now what is basically chi-square distribution we are using for the variance of the sample? If suppose a sample of size small n is used having a mean, mu and sigma square as variance, so this x is dependent upon n, mu comma sigma square normal distribution. Now if a sample of size n has a variance s square, then we proceed to consider the distribution having a new random variable. This is a new random variable that will be basically our chi-square distribution. So if we do the difference of the mean and square it, and then we further distribute into two parts and we open it, we get two terms over here. One is summation xi minus x bar whole square plus n into x bar minus mu whole square. X bar is the mean of the sample. This is mean of sample and this is mean of source. So if we divide these, we are getting this relationship. In this relationship, this is our what is random variable that has been distributed into two parts. One is n minus 1 s square by sigma square, that is basically referred as chi square, and this is what is called as square of z. So square of z or chi square. These are two terms over here which can be seen in two distribution. One is called as chi square distribution and other is called as t distribution. That is what we see over here, that this term is a chi square random variable with n degrees of freedom. So it is noticed that chi square random variable with n degrees of freedom partitioned into two components. One was chi square and other was z square with 1 degree of freedom. So this was chi square and the other was z square. To formalize this, we get a distribution over here. A relationship of a transformed variable chi square, which is a chi square is a transformed variable that is a function of s square, and we are using this as a new random variable. Now relationship of this with respect to probability will have such shape, and this alpha is marked at a particular point where chi square naught is a point. If suppose we are looking for the probability of chi square more than chi square naught, then what will be this value? This is nothing but alpha at a particular value of degrees of freedom n minus 1. So for a particular value of degrees of freedom n minus 1, we have this relationship which is available in the statistical tables of chi square distribution. Look at the table of chi square distribution. So if we see chi square distribution here, this alpha is marked over here. So this point is generally called as chi square alpha, which referred as alpha is nothing but the probability of chi square more than chi square alpha, or I was writing is. So this first row represent the degrees of freedom, first column represent degrees of freedom, and first row represent probability alpha, and all these values are nothing but chi square alpha. So these tables are relationship between chi square alpha, alpha and nu. So this way we can take the help of, this is nothing but probability of s square more than s square alpha. So this chi square is nothing but n minus 1 s square upon sigma square. So this was all about chi square distribution. So chi square distribution is nothing but a transformed distribution. Suppose we are looking for the relationship s square and probability. So we will transform into a distribution called as chi square and probability. That is a better shape and available over here. So taking the help from this distribution, we can solve the problems based on this distribution. So problems of relationship of variance with respect to probability can be solved based on the chi square distribution. This is called as chi squared distribution. Let's have this problem. A manufacturer of a car batteries guarantees that batteries will last on an average 3 years with a standard deviation of 1 year. So they are giving us the source properties. So source properties, mean is 3 years and standard deviation is 1 year. So this x, which is a battery life, belongs to a normal distribution as in 3 and 1, which is mu and sigma square. If suppose 5 batteries are tested, sample, size n equal to 5 with a set of values 1.9, 2.4, 3.0, 3.5 and 4.2. So if we have these 5 values, should the manufacturer still be convinced that batteries have a standard deviation of 1 year? So they want to know whether this sample has the variance 1. So they want to compare S square, which you will calculate here, sigma xi minus x bar whole square upon n minus 1. If you calculate this, then you have to compare whether it is sigma square as 1 or it is something different, assuming that battery life follows normal distribution, which we had already assumed. So in this case, your distribution will be between S square and the probability. You have to see that whether S square is 1 or else. So your null hypothesis S square is 1, or your alternate hypothesis that S square is not 1. So not 1, it can be higher, it can be lower. So you have to define the acceptance zone and critical zone. Critical zone will be on both sides, acceptance zone will be on this side. But before that, you have to transform into chi-square distribution. When you will transform into chi-square distribution, have to calculate chi-square for the sample. Chi-square for the sample will be n minus 1 S square upon sigma square. S square can be calculated from this. So the standard deviation what we are getting S square as from this is S as 0.9028. So S square will be something like 0.815. So this will be 5 minus 1 into 0.815 divided by 1.0. So that will be 3.25. So if chi-square is 3.25, we have to see where does it lie. So the probabilities of getting this is over the chi-square distribution. If this is our chi-square distribution, which we see over here, this is chi-square. So if we put a lower bound and upper bound values, and we see where this 3.25 lies, for this we have to set a chi-square at 0.025 suppose, and chi-square at 0.975s. Suppose alpha is 0.05 as a critical zone. So if this is a critical zone, we will set a value where it will lie. So these values we can pick up from the table, and we have to see where this value is. If this value is between these two, or we have to decide what is the value of probability that chi-square will be more than 3.25. So if this probability we see from the, for new S4, if we see 3.25, it is 3.327, 357 here and 2.0. So it will be somewhere over here. That will give us an idea that the probability will be 0.6 something. So this will give us a value approximately at over here, and this value comes as 0.60 approximately. So this will be 0.60 approximately, which gives an idea that the calculated value is almost giving the same variance of the source. If this value, which we call as p value, less than 0.025 on either side, if this value was over here or here, then idea was different. So this is how we can apply chi-square distribution. From the same problem, if suppose I want to know what is the probability that the sample variance will be more than 3.357. So in this case, what we will do is we will calculate a chi-square calculated, that will be nothing but n minus 1 s square upon sigma square. So this is 4 multiplied 3.357, that will give us a value as 13. So something like this we are getting here. So over the chi-square distribution we have to see where this point is, which is chi-square is 13.428. So what will be the value of alpha? To find out this value, this will be nothing but value of alpha, which will be similar as p-value of chi-square more than chi-square calculated based on this sample. So this value of alpha we can pick up from the table with degrees of freedom 5.1 is 4. So we will go to the table of chi-square distribution and we will see the value 13.428. So now in this case, for with respect to 4, the value 13.428 will be somewhere here. So it will be less than 0.001 but more than 0.005. So it will be, let's have 0.009 for example. So for nu equal to 4, we are coming up to this particular point, this point over here. So in this case, this probability will be, as per table of chi-square distribution, this alpha will be approximately 0.009. This is how we can solve the problem for chi-square distribution.